Okay, this video is about indicator variables and wraps up what we'll study about regression in this class. First, let's define indicator variables. Many books call these dummy variables. These are the tools that we use to incorporate categorical data into regression models. If you think about the past 7 videos, they all had one thing in common. The x variables were all quantitative. They were numbers, and they could do all the things that numbers can do, like have a sample mean and standard deviation. Indicator variables, usually called I, open the door to including categorical data into our regression. Now we can have variables like gender, religion, favorite ice cream flavor, and so on. We create indicator variables for specific categories like female or Christian. An indicator variable can only be equal to 0 or 1. The variable equals 1 if our data point belongs to that category, and it equals 0 if it doesn't belong. I like to think of these as 1s and 0s like on-off switches. I imagine the variable resting at 0, or the off mode, until we notice that an observation falls into its category, and then it turns on, and the variable becomes equal to 1. Anyway, if our categorical variable has k different possible categories, then we need k-1 indicator variables to define it. Let's suppose that a person's religion is going to be included into our regression model, and religion has 4 different categories: Buddhist, Christian, Islam, and other. Since there are 4 possible categories, we need 3 indicators to define it. Now, we need to pick any 3 of the categories. For this example, I chose Buddhist, Christian, and other. So I create a variable called b, which is equal to 1 if a person is Buddhist and 0 otherwise. And I create a variable called c, which is equal to 1 if the person is Christian and 0 otherwise. And I create a variable called o, which is equal to 1 if the person is other and 0 otherwise. Here are the first few rows of our data set showing each person's religion. If you tried doing a regression with this data, then the computer would give an error message because it can't accept words and text as input, only numbers. So we have to make 3 columns, one for each indicator variable defined in the past slide. The first person is Christian, so they get a 1 for variable c. And since they are Christian, then they are not Buddhist and not other, so they get a 0 for these variables. The second person is other, so they get a 1 for variable o, and the rest are 0. The third person is Buddhist, so they get a 1 for variable b, and the rest are 0. And the fourth person is Islamic. So they are not Buddhist, not Christian, and not other. And this is why we only need k-1 indicator variables for k different categories. The last remaining category can be all 0s. And here are the rest of the lines of the data set. It is not allowed for any observation to belong to more than one category. For example, in this data set, it must be impossible for someone to have more than one religion. Okay, now that we know how to make indicator variables, let's see how they work in regression models. This data set is about car repairs, and the y variable is the time in hours time in hours needed to fix the car. The first x variable is quantitative, and it is the number of months. since the car's last repair. The second X variable is categorical and is about the type of problem the car has. And there are two possible categories, mechanical and electrical. To get a picture of what is going to happen, let's plot repair time versus months since last repair. Next, I'm going to color code the points according to repair type. In this graph, the red points represent electrical repairs and the blue points represent mechanical. Note that some of the points are doubled up. For example, this point above 8, this red point is covering a blue dot that also happens to be in the same place. So let me draw what is going to happen in the regression. The computer is going to calculate a best fit line going through the blue points and also a parallel best fit line going through the red points. Those should be parallel lines. The vertical distance between these lines represents the difference between mechanical and electrical repairs. And in the regression output, it will be the slope coefficient of the indicator variable. But first we need to make the indicator variable. Repair type has two possible categories, mechanical or electrical. So we only need one indicator variable. We need to choose one of the categories, so I'm going to pick electrical. So I'm going to make a variable that equals 1 if the repair is electrical and 0 otherwise. And here is the data after making the change to the indicator variable. And here is the multiple regression output for this data. Let's first notice that each variable is significantly related to repair time, and that the fit of the model is pretty good. But I want to focus on the slope coefficients to see what they mean. First, I want to find the regression equation for mechanical repairs. This would be the straight line going through the blue points in the graph that I showed a minute ago. So here is the best fit equation from the computer output. Just remember that electrical is an indicator variable that can only equal 0 or 1. And if the repair type is mechanical, then it equals 0, and we get this line equation. Now let's find the equation for electrical repairs. This time the indicator variable is equal to 1. And the overall effect is that the slope coefficient of the indicator variable is added into the intercept. This effectively raises the line by 1.26. And we can interpret that by saying that electrical repairs are expected to take 1.26 more hours than mechanical repairs, all else being equal. Now that we have a basic understanding of indicator variables, let's look at some of the other ideas in regression. In the past, I've always treated multicollinearity like it was a problem, but there are occasions where it can be useful. The data that you see here is a study about the factors that affect a person's salary, and the complete data set is not shown. So salary is the Y variable, and there are 3 X variables that may have an effect on it: education, experience, and gender. Education and experience are quantitative variables. Both are measured in years. Gender is an indicator variable that equals 0 if the person is female and 1 if the person is male. Clearly, the juiciest variable here is gender. If you do a study that shows that education and experience are related to salary, then people will yawn and say, well, of course they do, and then lose all interest. However, if you publish a report showing a systematic difference between male and female salaries, then that's a big deal, and probably a high-profile lawsuit too. So let's first look at the regression using only gender as the x variable. Here's the computer output, and I want to focus on the slope coefficient of gender. The slope is positive and greater than 20,000, and its p-value shows it is significant. Since the indicator variable equals 1 for men and 0 for women, this means that men make significantly higher salaries than women. The intercept, 76,189, represents the expected salary for women, or when the indicator variable equals 0. And the slope of 21,643 means that men's expected salaries are $21,643 higher than women's expected salaries. That's a big difference, and bad news for the company. It seems like gender discrimination is a big problem, and a lawsuit could be on its way. But before they call their lawyers, let's look at the multiple regression output using all 3 x variables. In this computer output, the difference in expected salaries between men and women is less than $2,000. And this difference is not significant. So what's happening here? Clearly, these x variables are correlated with each other if the slope coefficient changes that much after we put the other variables in the model. So multicollinearity has a strong presence in this data set. And I want to remind you about one of its effects. It adjusts slope coefficients for the presence of other x variables. So the slope coefficient for gender that we see in this output is the slope adjusted for education and experience. And what we see is that after taking education and experience into account, there is no significant effect on salary due to gender. We can also use the interpretation of the t-test to say the same thing. If we already know someone's education and experience, then learning their gender does not significantly improve our understanding of their salary. Now that we've come this far, let's use this data set to develop the best model for predicting a person's salary. Let's first look at some scatter plots to see if there are any nonlinear trends or possible interactions. The plot of salary versus gender shows very little, since gender can only equal 0 or 1. The plot of salary versus education looks a bit strange, possibly nonlinear, or it could be the result of an interaction. It's really hard to tell just by looking at the graph. But it does seem like something unusual is going on. And finally, the graph of salary versus experience seems pretty straightforward and linear. And what I'm going to do is throw the kitchen sink into this model. That means I'm going to put in lots of higher order terms and interactions, anything that might possibly end up as significant in the multiple regression model. From this large full model, I'm going to use backward selection to remove the useless variables one by one until we have only the important variables left. And this is the full model that I'm going to begin with. I've included the square terms for education and experience, as well as all possible two-way interaction variables. I could have used other variables such as education cubed or the three-way interaction variable, but it seemed extremely unlikely that they would be significant, and I don't want this to take all day long. I've already talked about backward selection in the multiple regression videos, and all the same rules apply, but we have to add a few new rules now that we've started using higher order terms for our models. First, I need to define the degree of a term. Degree is the sum of all the exponents of variables. For example, the degree of this term is 9, since we would add the powers of 3, 5, and 1. Degree is important to backward selection because we cannot remove any term, even if its p-value is not significant, if it is part of a higher degree term that is still in the model. For example, we could not remove x squared before x cubed, because x squared is a part of x cubed. And by that, I mean that x squared could be multiplied by x to make x cubed. And we also could not remove the interaction variable s squared times t before s squared times t squared. With this new rule for backward selection, let's see how our model does. Okay, here is the regression output for the full model that I showed a minute ago. Before we move on, I just want to point out that r squared is equal to 0.716. So the model has a moderately good fit. We need to find the variable with the largest p-value and remove it first. The largest p-value belongs to the interaction variable experience times gender. So we remove that variable and redo the regression to get this output. Now our largest p-value belongs to education squared. So that is the next variable to be removed. This is kind of a surprise since the scatter plot for education seemed nonlinear, but let's keep going. After removing education squared, we get this regression output. Now our largest p-value belongs to education. But this is where it gets interesting. According to our new rules of backward selection, we aren't allowed to remove education, which is degree 1, before any of these interaction variables involving education, which are degree 2. Since we cannot remove education, we must move on to the second largest p-value, which belongs to the interaction between education and experience. After removing that variable, we redo the regression and get this output. Once again, education is the largest p-value. But once again, we cannot remove it because of the interaction variable involving education. So we go on to the second largest p-value, which belongs to experience squared. And that is the next variable to be removed. After removing experience squared, we get this output. Once again, education is the largest p-value. And once again, we cannot remove it because of the interaction variable between education and gender. Furthermore, all of the other variables have p-values that are significant at 5% level. So nothing else will be removed, and this is our final model. I just want to point out that the r squared has decreased to 0.708, which is only barely less than the full model that we began with. So all the variables that we removed had almost no effect on salary. Now that we have our best model for predicting salary, let's interpret it to see what it means. First, the slope of experience is about 4,000, and we can interpret that the usual way. Each additional year of experience increases your expected salary by about $4,000, all else being equal. But when you look at the slopes of education and gender, you might get a little shocked. It looks like more education means less salary, and that men make $67,000 less than women. But these variables are tangled together by their interaction variable. So we can't just look at one slope coefficient separately. We have to look at the entire tangled mess as a whole, like we did in the last video. Let's begin analyzing the interaction by focusing on how education relates to salary. And here is the best fit equation from the computer output. Let's begin by putting every term without education out in front as the intercept, and then factor education out of the rest. Since education interacts with gender, its relationship with salary depends on the value of gender. Let's start with women. Their value for the indicator variable is 0. And the equation simplifies to this. Next, let's do men. Their value for the indicator variable is 1. And the equation simplifies to this. We can now see how the effect of education is different for men and women. Each additional year of education increases salary by over $4,000 for men. But for a woman, an additional year of education actually slightly decreases salary. At this point, we have to be a little bit careful about causality. It is tempting to think in terms like increased education causes lower salaries. And imagine some kind of monster company that is actively punishing female education. It is closer to the truth to say that there's a negative relationship between education and gender for women. For some reason, this company tends to pay its less educated women more than its well-educated women. We don't know why this is happening, and it doesn't necessarily have to be evil. For example, this company might need certain skilled workers who don't need a lot of education to do what they do, and perhaps most of these workers are women. Anyway, let's leave this speculation and keep doing the analysis. Next, let's focus on how gender relates to salary. So now let's put all the terms without gender out in front as the intercept, and factor gender out of the rest. Now we can see exactly how education affects the relationship between gender and salary. I'm going to use the spotlight method to highlight some common education levels from 9th grade up through the usual time it takes to get a master's degree. I put the results in this table. We can see that lower education values have negative slopes, meaning that women get paid more than men. And the lower that education goes, the more of an advantage that women have over men. And it's the opposite for higher education values. So let's find the exact point where education begins to favor men. This would mean that the slope of the gender variable must be positive. And this happens when education is greater than 14.77. This is basically what you'll be doing in your group project, but on a larger scale. I want you to begin with the kitchen sink, put in as many variables as you can into the model, then use backward selection to reduce it down to the best model, and then analyze your model. Finally, here is some computer output for a data set that is trying to predict a student's GPA. There are 3 X variables: gender, high school curriculum, and parents' education. The first 2 variables are categorical, and you can see their definitions here. The last variable is quantitative and is measured in years. The final regression model is shown here. And that is all you need to answer the 3 questions coming up. So good luck with that, and I'll see you in class.